Okay, so the one new piece that follows momentum and impulse is called the conservation of momentum. It's actually known as the law of conservation of momentum. But first, let's talk about what it means. Conservation means nothing is lost, right? If you're going to conserve the water, you're not going to waste or lose water. So when we talk about conservation of momentum, it means that, like, imagine a football player or a hockey player running or skating down a field, down a rink, and they smuck into a second one. Okay, in that collision, initially this first guy has some momentum, the second one is just standing there, no momentum. And then after the collision, like the second one might go flying off, the first one might rebound back. But what the conservation of momentum tells us is that the total momentum before the collision must equal the total momentum after the collision. Okay, so it's called the law of conservation of momentum. And because it's called a law, it's that word flags it to say it's always, 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 always true. It's not a theory, it's a law. So law of conservation of momentum. So whenever you see the word law, like Newton's law, Newton's three laws, universal law of gravitation, it means it always holds true. Okay, so the law of conservation of momentum simply is that the total momentum before a collision, the total momentum before, and I'm going to say an event, because sometimes it's not a collision, total momentum before an event, and I'll explain that as we go along when it's not a collision. Total momentum before an event must equal the total momentum after. Momentum cannot be created nor destroyed during the event. Okay, I'll add one more thing to that in a minute. But note, this is with an isolated system, so meaning that there's not anything else from the outside that's interfering here. Okay, the one other piece is the momentum between the objects within the system can be exchanged. So total momentum before an event must equal the total momentum after. Momentum can neither be created nor destroyed during an event, let's say, in an isolated system. In an isolated system, meaning there's nothing else except these objects that are colliding, that are interacting here. There's nobody else that's coming in to hit one or pull one away, okay? The objects within the system can exchange momentum. So it's not saying that each object will have exactly the same collision momentum as it did beforehand. It's saying the total before must be equal to the total after. So total initial momentum must equal total final. And I'd write the word momentum, except I'm at a page. Okay, so the way we would show that in equation is we would say the momentum of the first object, so m1v1 initially, before whatever happens, plus the momentum of the second object, m2v2 initial, plus the momentum of the third object, if there is one, plus the fourth, plus the fifth, ... Almost all the questions will only have two. A few will have three. Equals the momentum of the first one after, plus the momentum of the second one after, plus the momentum of the third one after, plus dot, dot, dot. Okay, so this is the equation that we will use for the law of conservation of momentum. We won't write the dot, dot, dots. We'll just write however many m1 v1s we need on either side. But really all it's saying is the momentum of the first plus the momentum of the second plus the momentum of however many others initially has to be equal to the total after. Okay, now really there's probably 4 different types of examples of collisions or events. So the first one is one object is moving and it smucks into moving and one, I should put a 1 here, eh? One object moving and one object at rest. Okay, so this would be like a car colliding with a parked car, or if you play pool, a ball rolling in and hitting a second ball that was stopped. Okay, the second type of collision, and that's a 1, is both objects are moving. And it could be that they're moving in opposite direction, like in a car crash. One could be going this way and one could be going this way. Could be that they're going one behind the other and the one from behind rear ends you. Okay, but in the beginning, both of them are moving initially. Both objects moving initially. Okay, a third one is that, like, so in both of these, I'm imagining that, like, you know, so here's an object, it strikes the second, it's moving this way, it strikes the second one, and then they go off. In the third one, the 2 objects, whether they're both moving or only one at the beginning, but after the collision, they stick together. So a third type is objects stick together after collision. Okay? And when that happens, it means the 2 of them have to have the same VF, and really they almost become like a single object because they're stuck together. And then the fourth type isn't really a collision, it's more of an explosion. And what I mean by that, it's like, it could be like a gun with a bullet inside, or with a dart or something inside, right? So initially they're both at rest, and afterwards the bullet goes this way and the gun goes that way, right? So in an explosion, things are at rest to begin with. It could be like 2 skaters standing on center ice, and then they push off each other. So initially they're at rest, and then afterwards one goes each way. Or it could be like you standing on a raft out in Killarney Lake, right? And you're just standing there, and then you jump off this way, and you know the raft's going to go that way. Okay, so that's what we mean when we talk about explosion ones, that initially the objects in the system are at rest, and then something happens and they go apart from each other. So today we're going to do examples of 2 of them, and then you'll do some practice, and then tomorrow we'll do the 2 more examples, and then you'll do some more practice. So example 1. Is a 100-kilogram cart traveling 24 meters per second. So again, I would tend to draw it. So a 100-kilogram cart traveling 24 meters per second east. So V1 initial, 24 meters per second, and it's east. Strikes an 80-kilogram cart initially at rest. So here's my 80-kilogram cart, and V2 initial is 0. And then it says, after the collision, the 100-kilogram cart is traveling 10 meters per second east. So after the collision, the V1 final is 10 meters per second still east. So it was big enough and going fast enough that it didn't lose all of its momentum. And it wants to know what's the velocity of the second cart, V2F equals question mark. So you write down your equation, m1v1 initial plus m2v2 initial, and we're going to run out of time, so I'll finish this in the next one, equals m1v1 final, m2v2 final.